Okay.
Okay, great. So let's welcome Rob, and he's obviously he's just arrived in Australia a couple of months now at Monash University. He was at Carleton University in Canada before, so it's fantastic to have him back, or now back in Australia, so he can and build up the AR VR community. And so he's going to talk about the work he's done, actually mostly in Canada, I guess. But
Yep.
yeah, do you need
This,
me to plug you in as well?
yeah, if you could, yeah, thank
Okay,
you.
sure.
Yeah, actually, I think everything in here was done in Canada.
Great,
Here we go. Yeah, okay.
great, perfect.
Just pull it in a bit snug there. Okay. Hey, hi everybody. So yeah, thanks for the introduction, Mark, and it's great to be here. I'm going to be talking about passive haptics, which Mark and others have talked about very briefly earlier on through this in the week, but I'll give you a little bit more information and specifically about some of the work that I've done in this space. Or I should be more accurate, say some of the work my students have done in this space. Give credit to the people who do the real work, right? Um, so why passive haptics? And Mark's made similar arguments earlier in the week that modern VR systems have very good visuals. Audio is essentially a solved problem if you want to call it that. Tracking fidelity has gotten very good. In contrast, and this is sort of an argument for haptics in general, physical interaction is comparatively limited. We get vibro-tactile buzzing in controllers, and that's pretty universal with all modern systems. But touch beyond that is very limited. And I think you'd all agree, or otherwise you probably wouldn't be at a week-long workshop on haptics, right? Um, so far we've been talking about a lot of approaches to this where you can simulate touch using sort of specialized hardware. And the question posed by passive haptics, how can we do this without complex hardware? Is there a way we can simulate touch without complex hardware? And this is great for somebody like me. I've got a background in computer science. I can't solder things, so anything I have ever soldered has literally gone up in smoke. And so for a software guy, there's different ways you can handle haptics. And Mark talked about some of these earlier in the week as well, and I'll talk about some of these a little bit more. But for somebody who's from a software perspective, how do you do this without having to dip too deeply into complex hardware? And this is kind of an interesting space for people with that kind of skill set to be in. So this is a little bit of a refresher because we've seen variations on these kinds of slides a few times now,
Mm.
and I think some of the figures might be even the same as what have showed up already. But as a quick refresher and to kind of make the case for this, so touch feedback comes from a variety of different sensors, receptors. I'm not going to list these all comprehensively, but we've got our cutaneous sensors and we've got kinesthetic sensors. And specifically, we've seen figures like this throughout the week a few times now, talking about how all these different receptors are responsible for the different ways we feel things. And you've got from tactile sensation of, from skin distortion and things like this, and sensing vibration and shape and texture versus kinesthetic, where it's coming from our muscles and our proprioception, this ability to sort of feel our relative position of our limbs in space and feel weight. And this is one of the things that makes haptics such a difficult problem to solve, is that most of the devices we've been seeing sort of, if you want to call it, attacks sort of one kind of receptor or another, right? You get something that will, like a phantom device, for example. We haven't seen these here, but I think you all know what a phantom is. These robot arms that they push back. Mark showed these early on in the week. These things sort of attack your kinesthetic sense, right? You have this robot arm that pushes back to kind of simulate this sense of this muscle action you get when you're lifting a weight or something like that. Versus the vibrotactile solutions or the ETAC solutions, things like this are attacking your cutaneous senses or various varying degrees, right? So you can get one or the other usually, and it's very hard to cover all of these. And you can find research prototypes that have tried to, very convincingly simulate multiple facets of touch. And usually they sort of can do one very well and maybe two pretty well. And then three is kind of the limit. And then beyond that, it's like, well, it gets very complicated to cover all of these. And so all these solutions are great for specific use cases. And if you design a system cleverly, you can work around these constraints and make a convincing sense of touch for a specific application. But if you want to simulate touch in general, it's very, very hard to do that. So this is where passive haptics come in. And basically the idea is, well, if I want to feel an object there, why don't I just put an object there? It's very, very simple concept, right? And if I want to have feel like there's a table in the environment, well, I could just put a table where I want my virtual table to be. And this is, like I say, technically, there's much less complexity here. And so this is great for primarily software people like me who can't solder things and can't build devices. So that's kind of the idea. So this is I'm not super thrilled about this categorization, but as sort of a rough idea of where these kind of different solutions fit on a complexity cost axis versus a richness or physicality axis. This is kind of roughly where you can imagine these different kinds of solutions sitting. And at one corner, you've got sort of your phantom-like devices or exoskeletons, like you see at the bottom. Have you seen a few examples of these earlier in the week as well? And some of the haptic gloves in kind of the middle there. Um, and arguably the ideal haptic interface is at the top left corner with very little mechanical complexity and cost and with very rich physical interaction, but this device doesn't exist yet. So this is where passive props come in. So basically what you have is a real physical object co-located with virtual objects. So there's, why are these not at the very far left side of mechanical complexity slash cost? Well, you still have to deal with things like tracking. You still have to track these objects, which introduces some complexity and some cost. So if you've got something like a complex optical tracking system like a Vicon, which some labs do, these are, if you haven't heard of these before, very expensive tracking systems that look for points of light. They use them in, for example, movie motion capture and things like that, for full body motion capture. If you have a system like that already, then the cost of passive haptics is very low. But if you don't have tracking systems, or even as simple as those Vive pucks, you can imagine attaching those to objects and again tracking a single object that way. But the orange category, I'm going to come back to that a little bit later. But this is sort of, I don't know if this term is really caught on or stuck, but in some of the work we've been looking at what I've called dynamic passive haptics, and essentially these are objects that can sort of minimally change shape, so that if you need I mean, for example, at the bottom center there, that you see this person holding this hinged panel thing. That's a device we invented that can kind of change shape from flat configuration like you see there, or it can sort of fold itself up like a book, or it can turn itself into a cylinder. So if you need a small range of different shapes that you can pick up in the environment. I need a hammer now, and it rolls itself into a cylinder. This is so you're not really. It's a little bit different than things sort of in the top right category there, in that you're not using the actuators in that to push back against the user. It's just sort of changing its shape, and then otherwise the physicality of it comes from the fact that there's just a different shaped object there now. So I'll talk about those a little bit later in some of the studies we've done in that area. Um, so really quick history of these, because this has been looked at for quite some time now. And I think it was Rob Lindemann who coined the term passive haptics in the first place. Um, and you can see some of the early studies done on this. I think I have a video on the next slide of one of these, but yeah, some of these you can see the bottom left. This was can you guess what they're doing in that study? This was arachnophobia therapy, and I had a video of this, and I ended up deleting it because it's quite really old. But you can find videos of people doing these kinds of experiments, and it's sort of like the Planck study that or the Planck game that you saw earlier in the week. And actually, that's pretty much exactly what this bottom right example is. But the idea being with exposure therapy, you expose people to the thing they're afraid of to varying degrees, and then try to kind of condition them to get better about it. In this case, spiders. And what they found works well here is sticking a big hairy rubber spider with a tracker on it. So when the person reaches out to touch the virtual spider, whoa, they actually feel a spider. The bottom right, I'll skip to there because I already mentioned that one. And I think Mark showed the full bird's eye view of this experiment earlier in the week, but you can kind of see they have this wall matching the shape of the virtual environment around them, made out of these styrofoam blocks, and then these wooden planks on the floor. And they're only this high, but basically the person feels like they're looking down into the pit. And like the what's it called? Richie's plank? Was it
British playing, that's
Richie's
right. Yeah.
plank? Yeah. Um, they kind of stand at the edge of this and they can feel their toes hanging over the edge and they feel like they're going to fall in. And this was done in presence experiments back in the 90s and early 2000s where they were looking at how much these different factors change people's presence. And in this case, one of the things they were looking at was heart rate as a proxy for presence. And lo and behold, they found when people stood at the edge of that plank and their toes hung over the edge, their heart rate went up a little bit because it was a little more engaging, a little more presence inducing than not having that plank. So various takes on this in the past. You can see the bottom, this one here, they're doing handwriting on a tracked panel. So they have a panel, they're tracking it. They have a stylus also tracked, and they can use that to do handwriting in VR. But I will show you this video here from this is from Kai 99, and you can see there we go.
Oh, I can put the volume up here.
Okay. They have trackers on both the panel and on your finger here.
The user interacts with GUI widgets simply by touching them with the index finger of the dominant hand. A red drop cursor indicates the location of the fingertip in the XY plane parallel to the surface of the path. An audible click sound is triggered when the user selects or releases a GUI widget. Active widgets change color whenever they are selected with the fingertip. We compare handheld windows to WorldFix windows. Handheld windows allow the user to manipulate widgets.
I think you get the idea. But the advantage of this, of course, you can carry this tangible panel with you in the virtual environment and get the benefits of things like, for example, it's very easy to select targets without having to worry about depth, for example, and you can actually feel the surface that you're striking. So some of the key insights that came out of this early work. Real physical objects provide rich cutaneous and kinesthetic cues for free. So free is a little bit debatable. It's assuming you already have a really good tracking system available, it could be quite expensive. But otherwise incorporating these kinds of props into virtual environments is comparatively easy. Sometimes, as I mentioned, you don't even need to track them all the time. Like I mentioned before, this example of a table in the environment. As long as you know the position of where the table is supposed to be, you know the dimensions of it. This is what the Richie's plank is doing, right? You see, if you might remember from the video at the very start, sort of calibrates with this controller, it calibrates the length of the plank and sets the position of the plank. But there's no active tracking happening there. They just set the position, said this is where the plank should be and how long it is, and the sort of setting the dimensions of it. And then after that, I mean, as long as you don't kick the actual plank out of the way, it just sort of lines up with where it's supposed to be. So sometimes you can get away without even tracking these things. This is what I mean by you get these rich cues because you're engaging all of the kinesthetic and cutaneous sense as much as you would in reality because again, there really is an object there, right? And you can get comparable performance to complex devices as well. The main challenge with these kinds of approaches, as you would imagine, is scalability. And so, this is great if you have exactly one plank or exactly one table or exactly one panel and one tracker available, this is great. But then as soon as you have 100 things that you want to interact with in the environment, then it doesn't scale, right? It gets very complex to deal with that. So fortunately, there have been approaches to handling this. So I'll talk about some of the work I've been doing in this area and a little bit of work that other people have done in this area. These are mostly along the lines of my research themes. So I've done a lot of work in selections. That is, how do you acquire objects in 3D environments or how do you acquire targets in 3D environments? And so naturally, at some point I looked at, well, what if you had haptic feedback? What if you provide a surface or similar to what Lindemann's work was doing, where you were actually tapping things on a panel? And then I looked at work around using a single physical surface to represent many virtual surfaces, and then a single object to represent multiple differently shaped objects, because that's kind of, in some sense, it's the holy grail of this area, right? It's what can I get away with a single tracked prop? Can I map that onto a whole bunch of virtual objects? That's what I would really like to be able to do, right? So let's talk a little bit about selection. And this work is going way back now. This is like this is stuff I was doing during and slightly after my PhDs. This is quite old now, but these different configurations you see here of well, at the left side there, so this is a predating Oculus, and things like that. So there weren't really cheap and readily available head-mounted displays at the time. So at the far left there, this was a so-called fish tank VR system that I built. And you can see there's an OptiTrack tracking system mounted on that rig. And you can see the bright dots are the retroreflective markers mounted on a stylus and on the stereo glasses the user's using. So the idea was that you would display stereo content. The shutter glasses would make it look 3D, and then you're updating the virtual head position lined up with the real head position. So they get this effect of things popping out of the screen or popping under the screen, but as they move their head around, it's as though it's actually there. And in that study, we were doing selection using the stylus in varying configurations. And I was actually at the time really interested in comparing this to mouse-based performance. It's a different conversation though. One of the things I honed in on here was how much does it matter if they can actually feel the surface. So there's the condition where targets are in the plane of the screen. Now people can actually feel the targets because they're actually striking the screen with the stylus, versus if they pop the targets out of the screen or use a ray to select targets that are presented on the far side of the screen. In the middle there, that was at York University's cave. And again, you can see I'm kind of hitting this plastic plexiglass panel, and as you can imagine, doing something similar where I've got these targets that kind of pop out of the out of the screen of the cave and are lined up with that plexiglass panel. And then again, it's the same kind of experiment at the far right there, but and again, it had a condition where the user is actually hitting the surface of the screen to kind of feel the targets, versus conditions where the targets were kind of floating in the air and they didn't get that tactile feedback. So I'm going over this quite quickly just because it's quite old, and I'm happy to chat more later if you want. Still have a couple of days here, but I'll very quickly mention this evaluation paradigm, because this is what these experiments were using. So if you haven't heard of Fitts law, it's a very well known UI design lesson about in some near large things are easy to acquire and take less time than large or than small far things. And that's what Fitts law is about. But for an evaluation paradigm, what's interesting about it is that you can model this with very good reliability, where if you look at this equation here, movement time is a linear regression model of this term called the index of difficulty, where A is sort of how far away the target is from the starting position of the cursor or hand or ray or whatever. And W is the size of the target. And the interpretation of this is that if A goes up, the target's getting farther away. The index of difficulty goes up as a term and makes it harder to select. And conversely, if W goes up, the target is getting larger, making it easier to hit, and index of difficulty goes down. And what's interesting about this is that you can model this as a linear regression model with amazing accuracy most of the time for techniques that conform to this. And mouse-based pointing, for example, that's, I think, what that particular example is from. It's highly linear. Movement time is highly linear with ID. But anyway, I did some work extending this to 3D applications, and the task that these things typically follow is this so-called reciprocal. I can do this with my fingers on this screen, I think. Oh, it's not going to work. Never mind. Too bad my performance was. But anyway, but this is the idea. You click these blue circles back and forth across the ring, and then from condition to condition, you vary the amplitude or the width of the targets to create a range of indices of difficulty. You record people's selection time, and then you plop it onto a model like that later on to see how well it fits. And this is really well established in the, well, I guess now also in the 3D world. I was going to say in the 2D user interface evaluation world, but increasingly in the 3D world as well. So here's the cave experiment, what this looked like from the other point of view. You can see the person's sitting here. You can see the plastic plexiglass panel. And we had conditions where the panel was either there or not. So basically the targets were always sort of at the same depth, either where, co-located with the panel like you see in the overhead view on the left there, or just the panel was removed entirely. And people would do this selection task of these circles across the ring like that. And we recorded movement time and things like that. And I'll come back to some results on that. Just sort of, I'm going to wrap up all these results in one shot. You could probably guess what the big picture result of all this is here. The fish tank VR setup, you saw two variations on this, one where the screen was kind of tipped on its back, and then a later version where it was sort of upright. And there's a whole bunch of experiments we did with this system, and I'm only just going to talk now about the one related to haptic feedback. And so you have these conditions where you can see this at the top right. That's that same selection task that you saw a couple slides back. But this is it's being rendered in stereo here. So if you're not used to looking at stereo imagery without glasses or filtering being done, this is what it looks like. You see both the left and right eye image overlaid on one another. But what this is showing you is that they are converging at the circle, at the peak where the targets were actually located, because that was actually in the plane of the screen, versus the image below that where you can see they're kind of crossing at some point, which is telling you that these were actually popping out of the screen. So what this would have looked like to the viewer is you would have had these targets sort of floating out in front of the screen here. And because that was tracking their head, you could kind of look around and it would appear like a stable object. So in the one condition, you can actually feel the screen surface when you're selecting with the stylus, and the other conditions you could not because they were just floating in the air. Yeah, and another variation on this where we were looking at how much do different depth cues matter or visual aids. So things like you can see the texture gradient gives you a perceptual cue that converges at depth. And so we had, untextured versus textured. Did lots of experiments with this kind of thing anyway. Yeah, okay. I probably don't need to show this video, but this is what this looked like from you can see he's acquiring the targets, and I think, yeah, he's in front of the screen here. So you can, for what he appears to be hitting the targets from what he's seeing.
So he's not touching the screen at all.
Not in this condition, but in a later condition he does. I think you see that in this video.
So because it's a fish tank VR, the 3D is the content looks like it's popping out of the screen.
Exactly.
And touches the space.
Yeah. And I think. And you can see how the viewpoint kind of moves a little bit. That's from his head motions updating the view. I think this next one might be, that's at the screen surface. So he's actually touching the screen now, very briefly. So anyway, that's kind of what these all looked like. Come back. I don't know if I just might have messed up the zoom.
I can check. I'm still seeing.
Still seeing it? Okay,
yeah,
good. Good. So a few results that came out of this. The plot on the left here, this blue line, that was the touch condition. Don't worry about the rest. The rest is not really relevant for this talk. But the key thing here is this blue line. That was the touch condition on the screen surface. And the target height, that was how far the target was popped out of the screen. So 0 means at the surface of the screen. That's the leftmost column there. And then target height 4, 6, 8. This sort of targets were about here, here, and here, 4, 6, and 8 centimeters above the surface of the screen. And you can see immediately what happens from 0 to 4, this drop. By the way, higher is better on this metric. This is throughput. Higher is better. So performance drops from the screen surface to just in the air, and it's relatively flat after that. It dips down a little bit after that. Because there's other things going on here as well. Like, for example, stereo convergence accommodation mismatches get worse the further away from the screen surface these targets get. But this is a pretty small range, so we didn't think that would be too pronounced here. But you can see the impact of the absence of tactile feedback right away. And on the far right side here, that was from a later experiment. And you can see that depending on how far the targets were popped out of the screen, you sort of had a much less variability in selection coordinate depth. Where basically every dot here is selection coordinate, somewhere where they clicked the stylus. And it gets kind of, unsurprisingly, it gets a little bit flatter the closer to the screen surface, but also less variability away from the screen surface as well, which is interesting. They had better ability to detect where things were in depth. So yeah, touch matters a lot. We got performance close to a mouse when the screen surface was there. And as I mentioned already, a big drop in performance from when you had contact feedback to not having it, and less variability in selection coordinate depth with tactile cues. So I'll move on to another a little bit more recent stuff here. And Mark's again talked a little bit about some of this earlier in the week, but it turns out that vision dominates a lot of what we understand in VR, and what this means is we can actually sort of hack our perceptual system with visual cues. So we can fake out our vestibular and proprioceptive cues by showing this is how things like pseudo haptics saw earlier, this idea that if I pick up a virtual object and it kind of lags behind my hand, I get this sensation of it, that it's got like this weight implied to it, right? So things like that. There's lots of examples of this in the VR literature, and people in psychology have been looking at this even longer than people in the VR world have. And I'll show a brief example of this on the next slide. But if you've ever heard of prism adaptation, does this ring a bell? Have you heard of this before? It's the idea that you can sort of remap people's perception by, for example, offsetting their hand from its actual position optically. And so this has, again, been done for a long time in psychology. And in VR, we see this done things like changing your arm length or changing the environment's shape or size. You might have heard of redirected walking. I'll show what that looks like briefly in a minute. But just if you've never heard of prism adaptation before, show this very briefly here. So the idea is that
now the visual field
I'll
is
let her
shifted,
talk.
but her motor system has not registered this shift. You can see that she does not point straight, but point to the right side of the pen and curves back at the pen. After several trials, she can point straight to the pen without correction. This means that her motor system has adapted to the visual input. Well, this is prism adaptation. All right, let's take the goggle off. Once the goggle is removed, the visual system receives the normal vision again. However, the motor system has not registered this change. Now you see she does not point straight, but point to the left side of the pen and corrects herself back at the pen. This is called after effect. This prism after effect is what we want.
Yeah, so it's kind of interesting, right? So you can adapt to these displaced frames of reference. And this works in VR too, by the way. And then you have to adapt back to normal afterwards. So here's a couple of VR examples. The one on the left here is, I think this is one of the first of these, was redirected touching. And you can see that what the user is doing here is touching this box, and they're tracking the hand, and they're presenting some kind of cursor or virtual hand proxy in the VR environment. But what you can see, they really want to feel that bump on the surface of that box, but that bump isn't really there, right? But you can see he's really looking for it, right? And so this is this idea of what you show them in VR can sort of fake out what they see in reality. This is if you haven't heard of redirected walking, this is playing? There it goes. Okay, this is what I wanted to show. Actually, I picked a haptics example of redirected walking. You can see this so-called unlimited corridor. You can see as the user's walking along, he's actually walking along an arc, but he perceives himself as walking along a straight wall. And there's a tactile element to this one too, right? Because he's actually feeling the wall as he does this. And then theoretically, you can do this unlimited. That's the name. And so they're applying different versions of redirected walking here. With it uses things like scaling your motions so that you move farther virtually than you're physically moving, or curvature accelerations that you walk in arcs instead of straight lines, things like that. It lets you purpose a smaller virtual space and really physical, or sorry, larger virtual space than physical space you have available to you. So these kinds of perceptual illusions are a pretty exciting area to be in. Um, I've tried a variation of this unlimited corridor actually in Takuji Narumi's lab, who's one of the authors of this paper. And essentially what he'd show you is he had a table, just a table like this in his lab. And he'd say, walk around the table running your finger along the corridor like this. And what he'd show you is the table in VR would either match the physical table, or it would suddenly change shape to be a triangle-shaped table or a pentagonal five-sided shaped table. And you'd believe that that was actually what you were touching as you walked around this thing in VR. So it's a similar idea to the unlimited corridor here. So some of the work I've done in this area, or again, more accurately, my students have done in this area, we were looking at what we called warped virtual surfaces. And the idea was, it goes back to similar ideas to what Lindemann and others had done back in the late 90s. Well, let's just track a panel. And at this point, we had this very nice, not Wacom, but very similar kind of tablet. And we stuck a Vive tracker on it. And the idea was that it was this very good resolution digitizer, probably better resolution digitizer in the tracking panel than the tracking systems of the time. And what we want to do is, well, what if you wanted to scale this panel so that you could have a virtually larger tangible surface? So maybe you want to do things like in any of these modern VR systems, you get things like these menu systems and things like that when you start them up. And what if you wanted to hold a relatively small tangible surface like this tablet and use that as a proxy for a much larger virtual surface, so you get tangible cues from this thing. This is the idea. So we were scaling the tablet virtually and applying gain to the cursor motion by the stylus. The stylus was actually not tracked at all. The stylus position came exclusively from the digitizer of the Wacom tablet here. So again, that task probably looks familiar. It's once again that same Fitts law reciprocal selection task. And what we wanted to do is look at, basically we wanted to know if scaling the virtual tablet was going to affect performance or not. And specifically what we were hoping was that it would not. In other words, that people could do this without it harming their ability to use the system. And so we had 8 different scale factors ranging from 1 to 1 up to scaling at 2.4 times the size of the tablet. So that was, from about this to about like that kind of thing. And we actually did, normally here in this kind of work, you would do tests like ANOVA, I know about these, to look for statistically significant differences between conditions. And in this case, we did what's called a non-inferiority test, which is sort of the opposite. It's looking for statistical sameness. And it's something that, for example, drug companies use when they want to test a new drug and show that it's not worse than a pre-existing drug to do the same kind of thing. And so basically we're looking for a statistical sameness of our conditions across scale factor here. And that's actually what we did end up finding in this case. So these scores all look very similar to one another across scale factor, and they, statistics told us that they were indeed, for all intents and purposes, the same. So that was kind of good news for us. And we wanted to see, well, how far can we really push this? Like, what if you want to have a smartphone in VR? And at the time, HTC was plugging this smartphone-based control for the version of the Vive, for some version of the Vive. And we thought, well, what if you wanted to use this and scale it up to arbitrary sizes? And so we did a similar kind of experiment. I'll show what this looked like, just because I'm really continue to be amazed at what this guy, the student who did this work, pulled off technically here. He had, I should stop this for 1 second and preface this by saying this was during the pandemic, or right after the pandemic started. And this was a Ukrainian student who went back to Ukraine when he was starting his study, and so he couldn't take an Oculus device with him to go there. So he says, well, let's do it with a smartphone VR device, like a Google Cardboard. but he was already kind of committed to this direction of tracking a smartphone or tracking this secondary surface. So he basically had, as you can see, two smartphones. One is actually the VR device, if the video plays. Come on.
Playing from YouTube.
I think this one is local, I think. Let me try this school. Oh, there it goes. Okay. So you had two smartphones. One was actually acting as the VR device, and the other's acting as the input device. And he was tracking this QR code from the VR device. And you can see as soon as it sees that, it's going to start showing the VR environment. Here it goes. There. And then you can see what the VR view looked like. And he was tracking the secondary smartphone using that QR code or fiducial marker. And there, once again, he's doing that same kind of Fitts law tapping task on there. And you can see it's reflecting that in VR. So this was a really cool technical accomplishment to get all this to work. You see there's a bit of latency in it, which isn't surprising, but and he looked at this across these scale factors. And this time we did find differences based on scale factor, which there's different reasons that might be, but it kind of suggests there's limits.
Was he using the phone vibrator to provide the input as well? And the phone he was holding in his hand, he had the vibration, because that would be a nice thing to do as well.
I think he was, but I can't remember.
Okay.
Yeah, but that's a good point.
Yeah.
So it turns out, yeah, you can do this to a point. You can scale these things. What we also found, the participants were largely unaware of the scaling, which is kind of also good news. And when you want to do a perceptual illusion, the hope is that people aren't aware of the trick, right? Yeah, and so it didn't work as well for the smartphone, and we never really dug into that. You know, the student graduated and moved on, and the project kind of died at that point. But a little bit too bad. Maybe it's something worth revisiting someday. Yeah, what happened here? My slides are out of order. Yeah, okay. This is what I wanted. So we're going to talk. The last thing I want to talk about is mapping single objects onto multiple shapes and even positions. And sort of this is a really good example from Kai a few years back, where they're or sorry, this is still surfaces. So this is kind of where you want to be able to go with this, is have a relatively few surfaces that map onto a bunch of different surfaces in VR. And you can see he's touching these relatively few spots, and it's providing tactile feedback for lots of different things in VR by redirecting his hand motion.
That dome he's sitting inside, that provides all the passive haptic stuff.
Yep.
So if you're touching a physical round button, somewhere inside that dome there'll be a round button, and it redirects your hands to the round button.
You could, yeah, but in this one, I don't think they didn't actually have a matching prop. It's just sort of just like you're sort of just touching the surfaces.
Oh, okay.
Yeah, but they were.
And the surfaces are all different angles.
Yeah, yeah. So you get
your hand to the surface.
You get exactly.
Yeah.
You get redirected to a surface that sort of matches the angle of the thing you're going to touch in VR. So it's like it's really simple kind of approach. They're using eye tracking to figure out what thing you're likely to touch next. Okay, so I think I'm running out of time. So just to wrap this up, the last thing I'm going to talk about is how to map single props to multiple shapes. And I showed you an example from our lab from earlier on. I'll talk about that a little bit more now. So we saw redirected touch, and we found that heard that people are surprisingly tolerant of mismatches. So and this is sort of actually Mark was sort of just commenting on this, that they were sort of reaching to hit these surfaces in the sparse haptic proxy that sort of roughly approximate the orientation. They're not even trying to match the shape in that case. It's just sort of a flat surface that they're perceiving themselves as touching. And we heard similar things earlier in the week, that people are kind of tolerant of mismatches between these things. This is how some of these illusions work, like the different shaped table, right? You have a hard time telling that it isn't a triangular shaped table when you're seeing that, and your kinesthetic system and vestibular system can't resolve that to the well enough to figure out otherwise, right? So this is one example of mapping multiple, in this case, multiple different props, but repurposing them for a wide range of virtual objects. So this is pretty cool. You see he's hitting this ball in VR.
Oh,
And it's just a styrofoam ball hanging on a string with a tracker mounted on it. But then all the objects in the environment here, because now it's something else, and he's grabbed it. It's activating something. He's got to go into this escape pod now, and he goes to sit down in here. And you see there's this box that he sits down on, which is also tracked. And he gets redirected. Yeah, okay, this is winding back. So this earlier on, he was actually carrying that same box around with him, and he has to move it to a certain position. And they're using things like redirected walking. So he's ended up moving that box to exactly where it was. Then he goes through the environment some more. He comes back to reuse the same object later on. In this case, it's a chair the next time he gets to it. So it's really clever. You know, you have to script an environment like this very well, that things have to happen in a certain order, in a certain way for them to work, but you get the idea. So some of the work I've done in this area, we developed a couple of variations on this hinged kind of panel approach. And the first version of this is Haptobend, which you see here. And the idea of this was, and this was done actually in a student's course project, if you can believe it. And I talk about not having any soldering skills. And, you know, I come from a tech background. The guy who did this, John McClelland, was a business student, and he cranked this thing out in a semester, which was pretty amazing. Smart guy. But anyway, the original version of this was this hinged panel thing, and he had actuators inside so he could detect the rotation of the each panel. And then what we did with this was an elicitation study where we wanted to say, well, if we show you, you know, for example, a flashlight or a tablet or something, what configuration do you fold this thing into? And is there consistency in how people do this? Because then we can use that for the next step of this, which was to design a device that changes its own shape. So what this looked like was this, and you can see there, we showed them different objects, and they could kind of fold this thing into different configurations. When they were presented a target object, they would fold it. When they were satisfied, they pressed a button. You can see this is done in Unity, and as he folds the panels, he kind of in real time sees the configuration update to match. Gets to the point here. Here we go. Okay, so he's showing a flashlight, and what configuration do you roll that into? And then so he made it sort of this prism, and then he's satisfied with it. He presses a button, and then it sort of controls the object until the next trial, so you can see what that would look like and what it would feel like. And yeah, basically what we found was depending on the shapes shown here, there was greater or less degrees of consistency. For example, things like the sledgehammer and the flashlight, people tended to roll them up into cylindrical configurations. It got harder for smaller objects like the smartphone or the pen. The pen is, the scale is too far away from what the size of the pen was, right? And so even though it's kind of that tolerance of mismatch, we were kind of beyond the threshold at that point, let's say. Some of the other ones worked pretty well. Things like the tablets and that, people would pretty universally, you know, fold it flat, or for the larger tablet, they would roll the thing right out. But so we used this. You saw haptic retargeting earlier. I'm just going to very quickly show this again to remind you about this in case you forgot. But this is the idea.
Haptic retargeting is a technique that enables haptic feedback for multiple virtual objects using a
mute this because you've seen this before, but the idea is that you can redirect the user's hand to continually pick up the same object over and over again. And so we thought, if you had a shape-changing object, could you make retarget people to continually pick up the same object while it's changing shape between grasps, while they perceive themselves as picking up differently shaped objects in different locations? And so that's exactly what we did. This is Adaptic, this second version. This one's self actuates, and so it can change its own shape into different configurations. And you see a few options seen here. What we want to do is, as I said, use it with haptic retargeting to see if you could use this to repurpose onto multiple different shape props in different locations. And so what this looked like, music is on, turn that off. And this is actually quite an early video of this, so I probably should find a better one, but you can see the user sort of reaches out and touches the object, and then the device is changing shape. and they get something that is approximates it reasonably well in different locations. So we did a study with this. I won't go to have more details than I will go into here now, but the idea was that you showed them different objects like flashlights and books and things like that. The object would change, the device would change shapes to match that. Again, it's actuated in the sense that like it's changing shape, but the tactile feedback is coming from just the fact that there's a prop there, right? And we compared this to non-matching proxies and styrofoam balls. Found kind of things you'd expect, that people generally were happier with a matching or relatively close matching proxy. Our device and having, for example, we had matching props that were not shape changing, things like we had like a cylinder and a brick and things like that for other for non-actuated matching shapes. And people were happier with that than non-matching proxies, which is not surprising. But what was interesting about this was people were largely not aware of the retargeting happening. So the retargeting was going on, and I think a couple people kind of commented with, I think there was a little bit of a miscalibration with the hand tracker and things like that, but nobody actually figured out that their hand was being retargeted, we got similar kinds of performance between matched and non-matched shapes, but they generally preferred shape matching, which is, again, not super surprising. What else was interesting about it? So one thing that's worth commenting here, this is not sort of a magic bullet solution that will always work for passive props. It has a lot of limitations. It's haptic retargeting technique. Probably the most important one that is the subject of a lot of research is you kind of need to know the object people are going to grab before you can retarget them to it. So again, it works in these kind of scripted environments where if you know the next thing they're going to grasp, then you can do this. And that's why you might have noticed in the video, I won't roll back to it, but in the video, the user was always kind of putting their hand back to the starting ball, and then they would reach for the object. So we need to know where their hand is coming from and where it's going to in order to apply the technique. So there's lots of work being done in things like how to generalize this to make it work in environments. And there are people using things like AI models and eye tracking and things like that to try to predict what object are they going to grasp next, and we know where their hand is to start. Then we can work this in a more generalizable sort of way. But this is all open research still. Yeah, okay, so I think that's it for me pretty much. I'm at the end here. So it's yet another tool in your toolbox of what you can do with haptics. And again, I said I'm not somebody who's good with hardware. We did a little bit of hardware work in the stuff that I did, but it's mostly these were software-based techniques, and certainly sticking a plastic panel or a table is a really kind of lo-fi approach to this sort of thing, right? And then even more recently, I had a student doing work like this where he wanted a virtual replica of the lab, and he did it much like Richie's plank, this kind of calibration at the start. We say, I need to know where the table is. So we put the controller like this on the corners of the table, and then assuming the table doesn't move, now you've got a good tangible proxy for that table, right? So yeah, and you can enhance versatility of these kinds of approaches with perceptual illusions, and even a little bit of actuation can also further enhance versatility. So yeah, I hope you found this interesting. And yeah, give some credit to the people who did the real work here, all the grad students and postdocs, and yeah, happy to take questions, but maybe I can.
Do you want to talk about the conference?
Yeah, I have backup slides for this.
Yeah.
So, and as a side note, so we're hosting the IEEE Virtual Reality Conference, or sorry, IEEE Conference on Virtual Reality and 3D User Interfaces in Melbourne next year. And this is one of, if not arguably, the top event for virtual augmented mixed reality, 3D user interfaces, and even haptics. So if you're interested in this kind of topic, I think for a lot of you, this isn't too far of a trip to go some closer than others. But it's well worth coming to if this is a topic that's interesting to you. There's still time to submit papers. It's coming up at the end of August, and the other tracks, the posters, demos, and such will be announced fairly soon. But yeah, check it out. The website's live now, and
yeah, so if you're in Australia and interested in VR, this is definitely the place to be. And some of you are based in Melbourne, but it's only a short drive from Melbourne to Adelaide. So definitely think about, and even if you don't submit a full paper, there's other deadlines later, so demonstrations and posters and things like that. So, and even if you don't submit anything, you should definitely attend because this is the #1 VR conference. It'll probably be nearly 1,000 people attending.
Yeah.
So, and you'll see all the latest and greatest, including lots of amazing haptic
Yep.
technology. A lot of the manufacturers will bring their devices to show. So,
Tried so many great haptic toys over the
yeah,
years
yeah,
there. It's
definitely,
been
definitely.
yeah. And I think this is the first time it's ever been in
That's
Australia.
right. And it won't be back for another 10 years at least. So this might be the only chance you get to see it without having to spend thousands of dollars on travel. So definitely go. There's also opportunity to be student volunteers.
Yep.
So if you can't pay the registration, you can be a student volunteer and you can go for free and attend the conference as well. So Rob's one of the chairs. So definitely chat with him about that.
One other quick note too is as Mark,
somebody's asking if they can present online, if it's going to be a hybrid conference.
we're still ironing out details about that.
Still trying to work it out, but
Yeah.
I'm still a bit away. We'll see how it goes.
As Mark mentioned too, I've only recently arrived here since January, so I actually have a funded PhD position for if people are looking. I figure this might be a good place to plug it, and could be in haptics, could be in something 3D user interfaces, interaction, something like that. But if you're curious or know anybody who might be looking for PhD positions, feel free to pass that along. I'd be happy to chat with them or you. But anyway, if you've got questions, I'm happy to take those. Hope I didn't go too much over
So do
time.
you have any questions? Well, first, thanks, Rob. That was a great presentation. It's super important because as you can see from that, some of the technology was using quite simple, just pieces of cardboard and things like that, but we're able to provide a really good haptic sensation, but also very impressive. The end piece with the piece of, I don't know, we call your set of slats that were able to fold up. That was really amazing in terms of being able to um, configure different objects in different shapes. And there's been a lot of other work done in that area. Here at Adelaide, we did some work with redirected haptic touch with buttons. And we had a single panel that had 2 or 3 different size buttons and a slider. And then when you're in VR, you would see a whole control for like an aircraft. And when you went, and with lots of buttons and sliders, and when you went to touch the buttons and sliders, it would redirect your hand in the real world to the real slider. But in VR, your hand was going all over the place to different sliders, but it would still feel like you're touching the real slider. So it's a really powerful effect and really works really, really well. So does anybody have any questions for Rob right now?